Hey, what's up, guys? This is Chung. So today, let's take a look. This LeetCode problem number 1483, case ancestor of a tree node. So you're given like a tree with n nodes numbered from 0 to n minus 1, and the way the tree is described is within it's in a uh, parent list. Basically, the index the index is the current node, and the value of the parent I is the parent of the current index of the current node. And so the root node of the tree is node 0. And for this problem, you need to implement the functions get kth ancestor given like a node and the k number. You need to return the kth ancestor of the given node. And if there's no such ancestor, return -1, which means that if the case if the case is too big, and then you need to return -1. So for example, right, we have like this tree, and the way the tree is described is as in this node here. Sorry, the list parent node. So which means that for 0, node 0's parent is -1 because it doesn't have a parent, and node 1's parent is 0, right? And 2's parent is also 0, 3's parent is 1, 4, 5, and 6. And then to query the ancestor, right? So for example, the first one, the node we're trying to query is 3, and we're trying to find the first ancestor of the current node, which is 1. That's why the first one is just 1, and then 2 and 5, 5 and 2. So for node 5, the second ancestor is 0. That's why the second one is 0. And for third one, right, the sixth node, the third ancestor is it's -1 because this is the first one, the second one, but there's a third one, but there's no third parent. That's why it's returning -1. Yeah. So here are the constraints, right? So the total nodes could be this almost 10 to the power of 5, and the queries can be the same as this scale of the node. Yeah. Mm, yeah. So for this problem, I think first, we always try to solve it with the most naive way, right? So the most naive way is what? We try for each of the queries, uh, for each of the query, right? Uh, we use this value, we do a DFS, right? We do a DFS based on this parent node, right? And then we do the DFS for case times, right? And then the last time is the parent we are looking for. If there if we haven't find the if I've if we have reached the -1, right, before consuming all the case, then we need to return -1. That's the first brute force way, right? But with this constraint, as you guys can see, right, that's going to be a O of n square time time complexity, and this will lead to a TLE because and because if it's a balanced tree, right? I mean, of course, the search will be log n to search the parent, right? From the last one to the from the deepest child to the first to the node could be log n, but there could be always like a worst case scenario. So the worst case scenario is that this tree is extremely unbalanced, which means that there's only one line of node, right? If all the node only has one child. So in this case, it's a linear search. That's why it leads to this n square. So that's why we need to find like a better solution. Otherwise, it wouldn't be a hard problem. Okay. So to solve this problem, let me try to draw some examples. I'm going to remove this part. Hmm. I'm just going to use the extreme case, which is the a linear one, right? Because that's the problem we're trying to solve here. Uh, so let's say this is the current node. This is a node we're trying to find the parent. And let's assume k is equal to 10. So where's the answer, right? So the first parent is this one. The first one is the first one, second one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is here. This is the answer we're trying to find, right? This is the k equals to 10. How can we find this one, right? With in log n time. Basically, that's the goal we're trying to make here. I mean, so basically a technique we're using here is that it's called binary lifting. So binary lifting, what does it mean? It means that every time we'll always try to find the log n. We're trying to reduce the k by log k time so that we can reach our target in log n time. In log k time, right? So if we decide, okay, so let's say what is the value for log k? Of course, we need to do round it into the nearest integer. So so log 10 is what? Log 10 is equal to 3, right? Equals to 3. So if we remove log k from 10, so what's the remaining? The remaining is 2, right? Because 10 minus 2 to the power of 3 equals to 2. So that's why we need these two values, right? We need this 2 to the power of 3, and we also need this 2. So this 2 to the power of 3 is 8. So which means that, if we know the eighth parent for the current I, and then if we do a plus 2, then that's going to be our answer, right? So where's the 8? This is the 8. Okay, this is the 8. So from 8, if we jump like 2 more, so and then we'll find our final answer. So which means that we'll need to find the eighth parent for the current node. And to be able to find this eighth parent of the current node, we need to do some pre-process. So the way for each of the node, we're trying to pre-process the parent, uh, the parent that's equals to the power of 2. So which means for the current node, right? So for the current node, the first parent is 1. So basically let's say the 2 to the power of j, and j equals to 0 to m, right? And the m equals to the log of n, because for the extreme case, right? If everything is a linear, and then we only need like at most log n times of power to cover all the nodes because it's increased by 2, right? So basically, for the current node, right? So the power of 0 is 1. That's going to be the j equals to 1 in this case, right? So then for the j is equal to 2 is here. This is j equals to 2 because 1 to the power 2 to the power of 1 equals to 2. And when j is equal to 3, where is that? This is sorry, this is 0. I'm sorry. 0 and 1 because the j is starting from 0. Yeah. So the first one is the j is equal to 0. Second one is j equals to 1. And the third one, right? So 2 to the power of 3, 2 to the power of 2 is this one. And then j equal to 3 is here. Then 10, 11, 12, 13, 14, 15, 16. So this is j is equal to 4. Right? As you guys can see, we're jumping like 2 to the power. We always double our jumping, right? With the previously jumps, so that we can basically reach the last parent within log n time. And if we have like a pre-processed list or DP array for each of the nodes, we're maintaining like this kind of list, and this will help us to find the final answer within log k time. And why is that, right? So as you guys, I think we already have seen that. Assuming we have this list, so basically the DP I and J. This means the 2 to the power of J's parents of node I. That's the definition of the of this DP I and J. And assuming we have this like array here, how can we use this one to solve each query in log n time? Right? Assuming right we have 10. So every time we'll try to reach the log of the current case node. So for example, when k is equal to 10, so the first node will reach is 3, right? And which is this node, okay? Because then we'll try to remove the k. We'll try to remove the previously node from the k. Now the k will equals to 10 minus 8 is equal to 2. Since we already have like this node, so all is left is we just need to try to find the second pa parent for this current node. Okay, and then we do a log k again, right? So log 2 equals to what? Log 2 equals to 1 and do an int, right? Int log 2 is equal to 1. And then basically we'll find this node instead. That's gonna be our new base node. And then now the k is equal to 2 minus 1 equals to 1. Okay, because from here it means that we just need to find the first parent for the current node, right? Which is this one. That's gonna be our answer. So that's how we solve each queries in log k time, uh, given this kind of DP array here. Cool. So, and now the only thing left is that how can we build this DP I and J? Mm, so let's see. This is J equals to 4, right? So first, the DP I and J. So for I, it's up to it's almost to n, right? So this is kind of total of n. For j, we know that it's log n, right? Because the j we're storing actually the log, the basically this one represents 2 to the power of j. That's why we only need a log n space for the second dimension. So the state transition function is like this. So dp I and j equals to what? Equals to dp of this dp I j minus 1 and then j minus 1. So let me explain. So what does this mean? It means that, for the current I and j, let's say the I is I, right? It's the current I, and j is equal to 4. So this j is 4. This is I. So I and the 4 2 to the power of 4 parent is this one. That's gonna be our final answer. And what's the how can we use the dp previously state to calculate the current one? So what's the value for this one? For this j is equal to 3, right? So this dpi j minus 1 is the value of this one, right? Because this is I of 3. So I of 3 is this node. So from this node, what's the parents? How many nodes we need to skip to find this target from this parent from this node? It's what? One is 8. Is 8, right? So 8 is what? 8 is exactly the j minus 1. This is a 2 to the power of 3, which is equal to 8. That's what this dp function is telling us. Basically, from the previously state, from the I j minus 1 state, the value, the node from that state, we just need to find the 2 to the power of j minus 1's parent, and that will point into the same target. Yeah, so that's how we build this one. And as you guys can see, to build this one, since we have an n node, right? For each node, we're trying to build the up to log of n's parent. That's why the total time complexity to build this dp is n log n time. Cool. So I think that's everything we can talk about, and we can just start coding. So we have n and we just need the m, right? So for the m, we have int of log 2 to the power of n plus 1, right? Since we need to allocate an integer value of the second dimensions, we do a log of n and then we do a plus 1, making sure uh, we have enough space, right, for everything. And so since this is a class, and we're gonna do a self dp, right? So at the beginning, every place will have like -1 range of n, because the -1 means that the current element doesn't have the parents of the current element doesn't exist. Okay, so this is because since we're having a two-dimensional dp, and we're creating this dp assuming the worst case scenario. But for this one, let's say if for the best case scenario, we have like this n equals to what? Equal to 7, equals to 7. Uh, yeah, n equals to 7. Mm, so when n equals to 7 and the log 7 is 2 plus 1 is 3, so m equals to 3 here. But we're building like this one for all the for all the nodes, you know. So this one is fine because it has two parents in total. But for this one, you know, once we reach the first one, then for the second one, you know, we don't have enough. There's not enough parents, right, to populate. That's why, you know, at the beginning we use -1. So for the nodes that doesn't have this the parents for the current I and j. Okay, so all right, cool. So then I think we have a base case, right? So the base case is like this: for I in the range of n, you know, self.dp of I and 0. So this one is exactly the same as the parent I, right? Because the parent I is telling us the immediate parent for the current node, which is exactly the I and 0. And then from here we can build the rest, right? So for j, actually, so this is j. Yeah, maybe j is a little. Oh, sorry, this is I. Sorry, yeah. Range of 1 to m, right? Because since we already populate 0, and here we need to do a okay. Basically, this is a dp of I and j, right? It's equal to a self.dp self.dp I j minus 1 and then j minus 1. Okay, but here or no, we want to uh, I mean we want to do this when this when this the previous one is not it's not minus 1. Mm, yes, because if the previous one is a minus 1, right? Then it means that, you know, the previous one is not a valid it's not a valid node basically. If and for not for invalid nodes, there's no point of keep using keep populating the remaining nodes from the previously node. So basically, this index won't be a valid index because -1 is not a valid index. That's why we always check if this one is not a it's not a valid one. We simply skip that, and that's how we build this DP. And after this one, you know, so for each of the node, we have two to the power of j's in the parent for each node, and then we can use this one to quickly calculate the case ancestor. So the way we're calculating is that, you know, while k is greater than 0, right, and the node does not equal to -1, because if it's -1, we simply just return the node because we know, okay, we have reached the a node that doesn't have like a parent. So for so at each of the loop here, we always try to decrease the k by log k, log 2 of k, and by decreasing the log the node the k by 2 to the power of j, we have our node, the new node will becomes to the self.dp of the current node's j's parent, which will be the current base node, right? And then how many k's left? K left is 1. We just do this one, right? Of j. This is 2 to the power of j. And while this k has been decreased to 0, or the node has been, or we have reached a -1 node, then we can simply return the node. Yeah. So let's run the code. Accept it. Yeah, cool. So it passed, right? Yeah, so for the time complexity, right? So to put time complexity to build this one. So n log n. And to query case ancestor, this is only log n time, right? But we have k queries, that's why it's k log k. Yep, I think that's it for this problem. So for this problem, so we're learning like a new searching technique, right? Binary lifting, which means that for this kind of tree, we always store mm, the j's the 2 to the power of j's parent for each of the node. Because if we store this 2 to the power of j's parent for each node, basically we have the coverage for all the nodes in this uh, DP. Basically, from the current node, we can always uh, jump to any 2 to the power of j's parents, and from there we can do another jump, right? So basically, let's say we have like this kind of a line here, right? To find like a very far away point k here. So what can we do? We can always jump uh, the most that we can jump before k, right? Because let's say we jump to here first, because that's why we do we do a flooring here, because we know if we do another jump, right, by the another uh, uh, times by 2 will be over, because here if we jump another one, that will be over. That's why we stop here, and then from here we do another jump basically. So this is going to be our new range to jump, and then from here we also find like a smaller range to jump, maybe somewhere to here, because from if we do another jump from here, right, that means that we do a j which is greater than this one, it will be over k again, right? So and then we do this one jump here, and then this one, in the end we reach k. So we reduce the every time we reduce the distance from the current node to its parent by the log k. And so for us to be able to make this jump, we have to store uh, the informations. Since we have a new jump base node each time, we have to store this 2 to the power of j's parent for each of the nodes, so that we can make a jump at each of the new base. Yeah, I think that's going to be the idea or the technique we can learn from this problem. And I'll just stop here. Thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.